May I start my presentation?
Yes, you may.
Thank you. The title of my first report is Influence of Supporting Conditions on Longitudinal Fracture in Functionally Graded Frame under Periodic Dynamic Loading. The current article studies functionally graded load-carrying frames with longitudinal crack under periodic dynamic loading. Frames with three types of supporting conditions, namely 3 links, 2 links and a pinned support, and 2 links and a fixed support, are explored here. The principal aim is to evaluate the influence of the supporting conditions on longitudinal fracture in frames when the latter are acted upon by periodic dynamic loading induced by a motor installed on the horizontal member of frames. The maximum and minimum strain energy release rates are derived. The results indicate that the supporting conditions have significant influence on the longitudinal fracture in the frames under periodic dynamic load. Figure 1 illustrates the frames explored in the current article. 3 different support conditions are considered in order to explore their influence on the longitudinal fracture of frames. The frame in figure 1A, actually this frame on the screen, is supported by 3 links, 1 horizontal link and in point D2, and 2 vertical links in points D1 and D6. The frame in figure 1B, this one, is supported by 2 links, 1 vertical link in point D1 and 1 horizontal link in point D2 and 1 pinned support in point D6. The third type of support conditions is illustrated in figure 1C, this figure on the screen. The frame in this figure is supported by vertical and horizontal links in points B1 and D2, respectively. Besides, a fixed support is used in point D6. The part D4, D5 of the frame, vertical member, D4, D6, is split by a longitudinal crack. Actually, this is a vertical crack, as you can see on the screen. A periodic load acts in point D3 on the frame horizontal member. The first step in the analysis of the frame in figure 1 is to obtain the static vertical displacement of point D3 due to the weight of the motor. This is the motor that induces the periodic load. By employing the integrals of Maxwell-Morse, we obtain formula number 1. Formula number 1 for this displacement. In this formula, Ki is the curvature, Mi is the bending moment due to the virtual loading. Equations 2 and 3 are used for determining the curvature and the neutral axis coordinate. In formula number 2 and 3, B is the width, H is the thickness of the cross section. The stress sigma I is found by using formula number 4. In this formula, E is the modulus of elasticity. The strain is estimated by applying equation number 5. The axial force and the bending moment in equations 2 and 3 are generated by force F1. The latter is estimated by using equation number 7. In this equation, ME is the motor mass, G is the gravity acceleration. Equation 8 describes the variation of the modulus of elasticity along the thickness of the cross-section. In this formula, EC is the value of the modulus of elasticity at Z1 equal to 0. Beta is a parameter that this parameter actually controls the distribution. The static strain energy release rate induced by the weight of the motor is estimated by applying equation number 10 on your screen. Then equation number 12 is used to estimate the dynamic strain energy release rate induced by force F2. In this formula, GF2 is determined by applying equation number 10 by replacing of F1 with F2. The same replacement is done also in equations 1, 2, and 3. KDN is obtained by using formula number 13. In equation number 14, N is the number of revolutions per minute of the motor. The harmonic load acting on the frames is induced by a motor placed in section D3 of the horizontal member of the frames. The maximum and minimum strain energy release rate induced by the harmonic load are given by equations number 16 and 17. The strain energy release rate is derived also by applying equations number 18 and 19 for checkup of the solution. The strain energy due to force F1 is given by equation number 21. The strain energy is defined in terms of the specific strain energy by using equation number 22. Here, sigma I and epsilon I are defined by equations number 4 and 5. The strain energy due to force F2 is obtained by replacing of F1 with F2 in equation 22, and then analogical replacement is done also in equations number 1, 2, and 3. The strain energy release rate determined by equations number 18 and 19 confirm the strain energy release rate derived by equation 10. And actually this fact proves the correctness of the solution that is obtained in this article. The frame in figure 1b is explored next. The strain energy release rate is determined first for the load F1. The support conditions of the frame in figure 1b indicate that this frame has 1 degree of static indeterminacy. Therefore, the static indeterminacy has to be resolved before determining the strain energy release rate. The horizontal reaction in the pinned support in point D6 is taken as a hyperstatic unknown. The static indeterminacy is resolved by using equation number 23 on your screen. This equation actually expresses the fact that the strain energy has extremum for the actual value of the hyperstatic unknown. Then the strain energy release rate is derived by using equation number 10. A checkup of the solution is done by applying equation number 18. The strain energy release rate in the frame in figure 1b for the load F2 is determined to. Equation 24 is applied for dealing with static indeterminacy. After that, the strain energy release rate is derived by using equation number 10. The result is checked up by using equation number 19. Finally, the frame in figure 1c is explored. First, the static indeterminacy is treated. The frame in figure 1c has 2 degrees of static indeterminacy. The horizontal reaction and the moment in the fixed support in point D6 are taken as hyperstatic unknowns. Equations number 29 and 26 on your screen are used for resolving the static indeterminacy under load F1. Then equation 10 is applied for determining the strain energy release rate. And equation number 18 is used for verification. The treatment of static indeterminacy in the frame in figure 1c under load F2 is done via equations number 27 and 28. The strain energy release rate is determined by applying equation number 10. A checkup is done by equation number 90. The curves explored in the next 4 figures give clearness to the question for the effect of support conditions on the strain energy release rate in the frame under periodic dynamic loading. The combined influence of L1 to L2 ratio and the supporting conditions on the maximum strain energy release rate are shown in figure number 2. It can be seen in this figure that as the L1 to L2 ratio rises, the maximum strain energy release rate also rises because the frame rigidity is reducing. Concerning the influence of the supporting conditions, which actually is the main goal of the current study, one can see in figure number 2 that the maximum strain energy release rate reduces as the supporting conditions change consecutively from this in figure 1a via this depicted in figure 1b to that in figure 1c. Figure number 3 shows the influence which the A to L2 ratio has on the maximum strain energy release rate for the frame with the 3 types of supporting conditions defined in figure number 1. For all of the supporting conditions considered here, as the A to L2 ratio grows, so does the maximum strain energy release rate. The curves in figure 3 again show that the maximum strain energy release rate reduces when the supporting conditions change from this in figure 1a via this in figure 1b to that in figure 1c. The combined influence of H to B ratio and the type of supporting conditions on the maximum strain energy release rate in the frame are explored too. The findings are illustrated by the curves reported in figure number 4. As the H to B ratio grows, the maximum strain energy release rate reduces for all types of supporting conditions under consideration. In conclusion, it should be noted that the findings presented in this paper indicate that the strain energy release rate and the longitudinal fracture induced by periodic dynamic loadings can be regulated in a significant extent by the supporting conditions, actually by using some appropriate supporting conditions. Thank you for your attention.